Thank you everybody for joining us this afternoon. I have the pleasure of introducing Professor Raphael from University of Minnesota. He's in Minneapolis. If you're wondering, do you guys have multiple locations? Yes.
We do.
Okay.
Duluth.
Really?
Yeah.
Okay.
But they're different.
They have a great marathon.
Oh, yes.
Campus, yes.
Of course.
Correct, yes. So yeah, so good that we specified that this is University of Minnesota in Minneapolis. Professor Stern is an associate professor in the Department of Civil, Environmental, and Geodetic Engineering. Their department is the same as we have it at Ohio State. And he was a Ph.D. student at Urbana-Champaign. He was a visiting scholar over in Europe a little, and then Avandi. So very interesting. And then you got your career award from NSF, so congrats. And recently tenured, so also congrats. And he's gonna talk about interesting project about traffic management. So thank you for agreeing to visit us.
Thank you. Thank you very much, Stephanie, for inviting me. I'm very excited to be here. You'll see why in a minute. But it turns out Ohio State is a very important institution when it comes to traffic engineering. So I'm a traffic engineer. So if you look at the title of the talk, on traffic, impact of vehicle automation, on traffic flow management. That is what I look at. So over the last day and a half here, I've been really impressed with the facilities that you all have to study and understand vehicle dynamics. And what I want to, oh, that's on this page. I don't know. Good luck.
Yes.
Let's see. Hold on a second.
Sorry, because I don't know if slides are gonna have stuff in that.
There we go. They might. Wait a minute. Maybe.
No, that's okay.
What if I do this?
Sorry about that. I thought it was a smoother, easier thing. You can try. I don't know if the slide has stuff.
We are going to proceed, and then we will see if something shows up there, and I'll sketch it on the board if necessary.
Right.
Until then, excuse the distraction. Yeah, so I think about things perhaps a few levels more zoomed out. But it turns out that what happens in the vehicle level, what happens on the individual vehicle, actually matters at the traffic flow level. That is exactly that connection is what I want to talk about today. I am from the University of Minnesota. That block M is not meant to be offensive here. It is a different M. I've been told that you should be safe with that M right there. I know you guys claim ownership to the. I looked through my slides. I have very few references of the, so I did strike them out, but I was going to be respectful of this university's ownership of the. Okay, so let's talk about traffic flow management, and specifically, I want to talk about what's going to happen with vehicle automation. And there's, I guess, before we talk about what I want to talk about, I'm going to talk about what I'm not going to talk about. But I think this matters. If you're a traffic engineer, there's so many different ways that vehicle automation can fundamentally change the way we think about transportation, think about mobility at a much broader. One of the metrics that traffic engineers like to use is vehicle miles traveled, or VMT. And honestly, if you look at the literature, there is no good consensus on what will happen to vehicle miles traveled with automation. There's kind of two different scenarios that often are sort of debated, I'll say. The one scenario is, well, we have all these, pool shuttles. I will be going to the airport. I'm sure other people this afternoon are going to be headed from somewhere close to campus to the airport. We could share a ride, perhaps, an autonomous vehicle, and then my driver doesn't need to drive back, right? So that could potentially mean not only a reduction of, so for example, when Brian picked me up at the airport yesterday, that was an empty, so to speak, trip to come pick me up. That car was traveling, but not transporting me. It was transporting Brian. But if that were an autonomous vehicle, that could have then just sort of gone and taken the next drive for passenger somewhere else. So you could potentially see a reduction in vehicle miles traveled. The other way to think of this is it's really just a chauffeur, right? You've taken your own personal cost of time out of the equation you've effectively reduced the cost of travel. We've all gotten used to work from home. Why not work from car? Why not live, 3 hours, 2 hours away? Take your first couple of Zoom or team meetings on your commute in. If you're not doing the driving, it's what's the difference between the living room and your car, right? And then come into the office for only a few hours, and so you might see sort of acceleration, sprawl, and a great increase in that's true for land use then as well. Right? So the one example is, well, there's all these technologies, and I'll be talking about some of them in a couple minutes, that potentially could increase capacity, which means that instead of 3 lanes, you might only need 2 lanes. It's a lot of space, right? Also parking. Vehicles occupy a lot of space for parking. I spent time at Vanderbilt, and I remember there in Nashville, the statistic was really astounding to me. 23%, almost a quarter of their campus land area is dedicated to parking in a very high cost of living urban city. And if they didn't need as much parking, if autonomous vehicles just picked up and dropped off people, they could take that land and build, for example, graduate student housing, which was a really big problem for them at the time. So potentially more dense, but also again, things the autonomous vehicle being your chauffeur example. Why do you care about having nice housing close to campus when you could have housing 2 hours away and spend those 2 hours every morning on the commute getting work done, right? So again, 2 totally different scenarios that can play out here. The other one is safety. I'm not really going to talk about safety, but the exciting thing about safety is the top 2 are very speculative. What might happen? This one's pretty clear. There are, even before we reach full automation, there are nice safety features that come online. Robots are much harder to distract. They don't text while driving, or if they do, they multitask. And we can see some really nice improvements to safety. All right, so all these benefits here, when you think about it, all these benefits that we might see from automation, these are all benefits that matter to the occupants of the car, right? And so if you're trying to sell cars, that's great. But again, I'm looking at this as a civil engineer, as a traffic engineer, and I care about the management of these traffic flow systems at a slightly higher level, right? So I'm zooming out a couple of steps. And so I want to think about this not from the benefits to the occupants of the car, but the externalities of that car being autonomous on the overall traffic flow. One of the things that I find absolutely fascinating is traffic jams. I love traffic jams. Many of you I hate being in them or being part of them, but I really think they're fascinating. Many of you may have seen this before, but I think it's worth sort of highlighting. Over here on the left, we have a traffic jam in the wild. And now, this is on a roadway. You see here, in just a couple seconds, you'll see vehicles up there start to slow down, and then it sort of propagates backwards up the stream of traffic. And for a long time, there was a debate in the traffic engineering community. What was happening here, right? Is this due to external bottlenecks? Maybe the curve in the road, maybe there's glare on the road, causing drivers to brake. It was actually physicists in Japan who said, well, let's do what physicists like to do. Let's do an experiment and test this out. And so they created this scenario over here, which is pure car following, one vehicle driving behind the other. They've gotten rid of all of the messy sort of externalities of the world. No, police officer pulling people over, nothing sort of on the outside of the road. And they're really just looking at pure car following. And they start in an initial uniform flow, all the vehicles at the same speed, the same spacing, and relatively quickly a traffic jam emerges. And so we traffic engineers call these guys traffic jam, and that's because they arise for no apparently good reason. What's actually going on here, it has to do with how individual vehicles interact with each other, and the result of what we call string unstable traffic. The theory behind this was sort of largely developed in the 1960s, 70s, 80s, I think, 70s and 80s, 90s even. And the basic idea is you imagine a string of vehicles, so one following the other. They're all at an equilibrium flow, so they're all at the same speed, same spacing, no acceleration. And the question of string stability is not what happens to an individual vehicle after it brakes. Obviously, any reasonable vehicle would come back to its original starting speed or whatever, or its original speed. But what happens to that perturbation as it propagates from one vehicle to the next? In string unstable traffic, that perturbation amplifies until the first vehicle hits the brakes just a little bit, and then 10, 15, 20 vehicles down the line, you might be coming to a complete stop, got a full-blown stop go wave, as opposed to string stable traffic. That perturbation dissipates until you're 10, 15 cars further upstream, and you may not even notice that a car in front of you hit the brakes. All right. So there's been probably at this point 3 to 4 decades of solid work on how to overcome string instability. One very popular approach is things like platooning, interconnected systems where vehicles use something like DSRC or other communication to communicate with each other, tell each other what they're doing. And the cool thing about this is this has been around for quite a while, as you can tell from the vintage of those vehicles. This was done in the early 90s. I was still a toddler when this video was filmed. This is a bunch of Buick LeSabres in the early 1990s, driving at an incredibly tight inter-vehicle space headway. And you can take, traffic flow, basically have vehicles drive very safely at much closer headways, much smaller spacings, meaning that you can potentially increase the capacity of a single lane of traffic somewhere 2 to 3x. That's huge, right? If you took a 2-lane or a 3-lane highway in one direction, you reduce it down to a 1-lane road without actually doing anything in terms of, changing the infrastructure, or you take your 1-lane hub road, right, and you get the capacity of a 3-lane road, and all you've done is you've changed the way the vehicles drive. You're moving 3 times as many people on the same road. The challenge with this, though, is that connectivity requires everyone to, or platooning requires everyone to opt in. So you can't just do this if one or a small number of vehicles on the road want to do this. Everyone has to have the technology. Everyone's technology has to work, and you all have to agree on some standard platooning protocol to make this work. Now, to be clear, we, for a long time, have known that there are many people, there are many ways to increase the number of people that we get on the same lane of highway, right? So if you're a traffic engineer, instead of platooning, you can imagine carpooling, right? Just bring a friend along. You've now doubled the capacity of that road. Okay, if you're a fan of James Corden and his former show, right? You might know where this comes from. Okay, you pick up some more friends, now you have 4 times the capacity. Okay, so increasing capacity in terms of number of people per lane mile, not actually that difficult. We just don't seem to want to do it. This was, if you're an urban planner, you might have seen this before. This was famously sort of demonstrated by the city of Munster in Germany in the 1990s, early 90s, where they said, how many people can we get on, one of our city blocks, depending on what their mode of transportation is, right? And obviously, if everyone drives cars, the road is. Now, I hear a lot of, yeah, but congestion is not a problem. I'm not concerned about congestion. Soon we're going to have autonomous. And the problem with that statement is just by swapping them out for autonomous, I don't really see a difference, right? They still take up the same amount of road space. So just swapping them out for autonomous, and we've already sort of talked about all of the implications that autonomy might have on your travel behavior, there simply isn't enough road space. If we're running out of road space now, just upgrading to autonomy isn't quite going to do. So that's what I want to focus on for the next couple of minutes here is how can we get them, how are autonomous vehicles likely to drive? How is that going to impact the traffic flow and the corresponding capacity? And how can we improve that? Or, how can we deal with that as traffic engineers? Now, I think this crowd, I probably don't need to say this, but by saying autonomous cars, right, there's a whole bunch of different levels of autonomy. And different types of features, different driving capabilities come with different levels of autonomy, right? So we range from no autonomy, level 0, that's what I personally still drive, to low levels of autonomy, level 1, level 2, driver assistance, where you're taking some of the driving tasks and handing over to the vehicle at some stages, all the way up to full, high and full autonomy, where you have most or all of the driving tasks, most of the time or all of the time being done by the vehicle and not by the human. And so when we talk about autonomy, I want to make this distinction of when are we talking about low-level autonomy and when are we talking about high-level. Now we'll start with low-level. That's because that's what we already have, right? So if we look at driver assistance features, level 1, level 2, things like adaptive cruise control, I'm at the point where when I go to Canada Price or Hertz and rent a car, most of the time it has this feature. Until a little while ago, until recently, it was a premium feature on a luxury car. It's something that as a traffic engineer you would most pay for. But we're now at the point where that is simply not the case. And so My question is, how do low levels of autonomy, level 1, level 2 autonomy, behave when it comes to string stability? Remember, because string stability, that's the feature of the driving that tells us whether or not we're going to see those phantom jams or jams arise out for no good reason, or if they're going to have more of a jam smoothing property to get rid of those jams. Now, again, you can look to the literature, and there's decades of research dating back to the early 90s saying these things are actually relatively straightforward to design in a string stable fashion. There's, platoons of ACC vehicles may be unstable, but individual ACC vehicles likely can be designed quite easily to be string stable. You can see sort of like some sort of speed disturbance, right, from subsequent vehicles that generally tend to sort of dampen. Okay, great. So the literature says ACC vehicles are string stable. The problem was when I started this, it was sort of inspired by renting a couple of vehicles and noticing that they weren't always behaving exactly how I would expect them to behave if they're actually string stable. And so the way I wanted to address this is by getting data for how they behave, build a model for their behavior, and then analyze that model to understand what their behavior actually looks like. The model that I want to use here is sort of a common traffic level model. And the reason is you could invest a whole bunch of effort into a very high resolution vehicle dynamic model at the vehicle level, which is very valuable depending on what you want to do. But if you want to look at sort of traffic level effects, right? I want to look at entire corridor traffic level effects. I actually want a slightly lower resolution model. So I want to kind of sweep all of the nonlinearity that happens with your engine or with your engine through your transmission, all the way down to like tire pressure and road surface friction. I want to sweep all of that into just a relatively simple model that captures at a particle level sort of the acceleration and braking of a particle. And the models that are pretty common here in traffic engineering are called car following or microscopic models. They're ordinary differential equations that describe the acceleration of a vehicle as a function of the spacing available to it in front of it, the relative speed with the vehicle in front of it, is it catching up to or falling behind that vehicle, and the speed of the vehicle. All right, so it turns out that if you use these models and you want to ask the question of string stability in these car following models, well, that's actually pretty straightforward. You can inject a perturbation and watch what those perturbation dynamics look like. And if you're willing to accept linearization, so you look at the equilibrium and you look at the neighborhood of that equilibrium, and we could debate for hours what's a fair neighborhood of that equilibrium. But if you look at sort of linearization around equilibrium flow, remember equilibrium flow is same speed, same spacing, then you come up with this relatively nice, it has to do with basically the Bode plot and what perturbation frequencies are amplified, but you come up with this relatively nice characterization for whether or not a car following model is string stable. It turns out it only depends on the partial derivatives of the car following model itself with respect to the state variable. And so you get this lambda 2 value. If that lambda 2 value is less than 0, we have a string stable model. Generally, we're going to be dissipating or dampening waves. And if the lambda 2 is greater than 0, you're going to be amplifying perturbations or amplifying waves. And what's really nice about this is what it means is all we have to do is come up with a calibrated car following model that closely matches the actual vehicle behavior, again, at the vehicle level. And then, assuming we can take partial derivatives of that, we can analyze that and determine whether or not it's string stable. So the next step then is to collect data and understand what's going on here. So the goal is to basically come up with a car following model that describes the following behavior of the vehicle. And again, I'm sweeping a whole ton of nonlinearity with the rug here because I'm just looking at this as a particle. I'm looking at the vehicle as a particle that sort of travels along the road, and I want to be able to match the acceleration. And so the model that I'm going to use here is it's an optimal velocity type model coupled with a relative velocity component. Optimal velocity is somewhat of a misnomer. I think I prefer the word preferred velocity. Optimal velocity makes it sound like this is the optimal velocity to drive on based on some sort of optimization routine. That is not true. Really, these are constant time gap models. vehicles. So if you learned the 2 to 3 second rule in driver's ed, perhaps, right, follow 2 to 3 seconds behind the vehicle in front of you. That's exactly what this is. The faster you're going, the larger you want that gap to be. And it turns out if you look at that literature, that dates back, I don't know, 20, 30 years on string stability, that's exactly what they say to do. So there's reason to believe the car manufacturers won't necessarily tell you exactly what they do. In fact, I have spoken with some and they say, we don't remember, basically. Like from translating it from the original model, from the original controller down into the vehicle, there were so many modifications to make it work that they can't necessarily just write it down a closed form solution. But my guess is it's something pretty close to this. Okay. And then you got to go out and collect data. So the way we're going to do this is we're going to get 2 vehicles. The lead vehicle is going to drive with some predetermined speed, etc. Speed up, slow down. The following vehicle is going to drive with adaptive cruise control on and just follow the vehicle in front of it. Both of them are going to have high accuracy GPS receivers on them. And so we're going to have a good sense of, what the speed here, what the speed here, and what the spacing in between them. We can use that to get the relative speed. Just to give you a sense of what some of this data looks like, we start driving, we slow down, we speed up, etc. And then we watch what the following vehicle does. Remember, this following vehicle is just driving with adaptive cruise control. Okay, another experiment where we do some sharper braking events. And again, the following vehicle, there's a little bit of lag. These systems are working on relatively cheap sensors, so they're generally radar-based in the vehicles that we were testing. So there's a little bit of a lag, which then oftentimes means that they have to brake a little bit harder. And, well, that's going to lead us to our conclusions about their string stability. Okay. Now, first of all, I think a reasonable question here is, okay, we've taken an incredibly complex nonlinear vehicle dynamics, and we've swept it into a really simple linear, our following model. Is that a valid or is that a reasonable solution? So we can validate that model. At the top, what we see is for a sort of small part of that driving, in blue is the lead vehicle speed from the GPS. In what's that, orange? We can say orange is the following vehicle speed, again from the GPS, and in yellowish orange these are just the MATLAB default colors. So in yellowish orange is the speed that the model predicts, the calibrated model for that vehicle predicts. And if you look at it, it really nicely captures both the overshoot and the undershoot. And it actually was kind of surprising to me how accurately this simple model captures the super complex dynamics. We can also look at the spacing, inter-vehicle spacing. So in blue is the actual spacing, in orange is the simulated spacing. Not quite a perfect match, but it's really a pretty reasonably good match. It captures the shape of that really pretty well. It doesn't really underestimate the spacing. All right. So what does that tell me? That tells me that my modeling assumption that we're dealing with some sort of, our following model, that the controller is probably some sort of PID-like controller, proportional-like controller on a constant time gap is probably not that terrible of an assumption. And this model is probably reasonable. Okay, so I did this not just on one vehicle, I did this on a whole bunch of vehicles. Initially 7 different vehicles. I've done it on a couple other vehicles since. And remember, once we have, so for each of these vehicles, we can collect the data, then we can use that to calibrate this model. Once we have this model, we can look at the partial derivatives. This is a linear model. Partial derivatives are really easy to take. We have the values for all the parameters, and so we can easily compute whether or not this is string stable. And the result is that all of the vehicles we saw are string unstable. Now, for those of you here, there is an interesting second story here. And the second story to this is it really depends. You'll notice that all of the vehicles I originally tested are internal combustion engine vehicles. And there's a whole bunch of, I don't have to tell people hear this, lag, delay, nonlinearity that comes up. And so it wouldn't surprise me if, even if you're looking at the control theory from the 90s that says this is how you design string stable controllers, if actuating the car like that is actually not that straightforward. Because all of a sudden you have not just a differential equation, but you have a delayed differential equation, which is much uglier to deal. But when you start to look at vehicle electrification, one of the things that's really nice is you have full torque at low speeds, right? And so you get much more precise control of the vehicle. And so more recently, I went out and collected vehicle data on a production electric vehicle. Lead vehicle on the side, doesn't really matter if that's electric, but production electric vehicle on the right. And if you look at the same slowdown effect, on the right-hand side is an internal combustion engine vehicle. You see that overshoot both on the braking and accelerating. The left-hand side is the ACC vehicle in the electric vehicle ACC vehicle. And you see, yes, delayed, so still based on radar, still needs some sort of filtering and introduces a little bit of a lag, right? It's not instantaneous. That lag is a little shorter though, especially on the acceleration. And also that much less overshoot, or no overshoot on the braking, much less overshoot on the accelerating. Part of that is just regenerative braking is incredibly powerful, and so they can really hit the brakes if they need to. Okay, we looked at this a little bit. It turns out when you look at this, if you stare at this for long enough, you'll start to notice that you do better at the model, and you look at what the data in the model says. It turns out that that simple symmetric model that assumes the same braking and acceleration profile works relatively well for internal combustion engines, even though braking is a mechanical process, right? Whereas acceleration is a much more complicated process. But for these electric vehicles, that model simply didn't. So when you look at the spacing versus acceleration space, in blue is the data. And that model that I showed you, that like constant time gap, proportional control type model, is symmetric. So it assumes the same acceleration and braking behavior. But if you look at the data, that's not close to true, right? You can brake much faster than you can accelerate, even on an electric vehicle. And so we spent quite a bit of time building more complicated models that capture this behavior better. And that's really because when you want to do things like watch how these waves evolve, you actually need to have relatively good models of the individuals. So we introduced a couple different models. Here's one that worked particularly well. Yes, you're introducing more parameter values, but so obviously it's going to be better, right? But you can break that down into an acceleration, braking, and sort of coasting phase, and you can get much, much better model. Punchline here is, if you start to look at simulations of platoons of these EV ACC vehicles, you see much, much less overshoot, no overshoot on the braking, like almost wave dampening on the braking events, and much less overshoot on the acceleration events, meaning that likely these models suggest that low-level automated electric vehicles likely are about as close to string stable as you might expect, which is kind of exciting. All right, so we started with human drivers, string unstable, traffic jams emerge out of nowhere. You get something like a merge scenario. We then said maybe there's hope in automation. You look at the literature. Automation, low levels of automation ought to suggest be string stable. Maybe that will sort of start to ease some of this congestion. But when you look at the data, no, in fact, the ones that we have today are still, the AVs we have today are still string unstable. Though the ones that we're starting to get, the EV ACC vehicles, or the EV AVs, might be promising. If you're a traffic engineer, you've got intersections or merges, highways, corridors that you need to manage. What does all of this mean for capacity? And so what we've done is we've looked at a whole bunch of different simulations where we look at different levels of automation. So commercial ACC vehicles, as well as sort of theoretical look to the literature. What do people think autonomous vehicles ought to behave like in terms of reaction time? And we can look at what these traffic flow, what the capacity is on something like a merge bottleneck in simulation. All right, before we do that, I need to take a small detour. It's particularly cool to do this at OSU because this is all work that was done by an engineering professor here in the 1930s. Some of you may be familiar with this, but since we are on a vehicle and automotive center here. I'm not certain. So if you've seen this, you can tune out for a few seconds, but I want to make sure that we're all on the same page in terms of understanding how these results. All right, so on the left-hand side here, this is Professor Bruce Greenshields, who was a professor here in the 1930s, and he had this idea that traffic speed probably depends on traffic density. However, in the 1930s, there simply weren't that many cars. So when he went out to collect data, here he is collecting data, he observed a lot of vehicles at very low densities, so vehicles per mile of road, and correspondingly at high speeds. And then he observed one data point over here at a high density and a low speed. And what he did is what any good engineer would do. We fitted a linear regression to it, got a line. And so that gives us the Greenshields relationship, which is a linearly decreasing relationship between speed from some maximum speed at no density. So when there's no vehicles on the road, traffic flows at the maximum speed. Maybe that's the speed limit, maybe it's a little above the speed limit, down to when there's all the vehicles on the roadway and it becomes a parking lot and traffic flows at no speed. So if you know this and you know from fluid mechanics fundamental properties of flow, such as that the flow, vehicles per hour, is the average speed, miles per hour times the average density, vehicles per mile, you can get a low density relationship. And if you assume that constantly linearly decreasing speed density relationship, you come up with this parabolic low density relationship. There's a couple of quantities here that are important. We've got a critical density here. That's the density where we go from free flow to congestion. And at that critical density, we see our maximum sustained hourly flow rate, or our capacity. And that number, rather, those two numbers are crucial for highway management. Because depending on what those numbers are, that determines how many vehicles per hour you can get across your pavement, and at what density things are going to start to become problematic. Now, if you look at data, it turns out that Greenshields was close, but not quite right. In reality, it's more like a triangular fundamental diagram. Vehicles in congestion generally don't really interact with each other, and so they're all kind of going at the same speed, regardless of the density, up until some critical density. In fact, if you look at actual data, which we'll look at in a minute here, you'll see that this is typically a lopsided triangle. So it's not a isosceles triangle like this, but it's some sort of lopsided triangle, where the critical density is typically quarter or so of the maximum. All right, so back to what we want to do now that we understand the fundamental diagram. If we look in simulation and we look at fully automated vehicles, it turns out that not considering connectivity, remember connectivity gave us like 2 to 3x. Not considering connectivity, we see maybe, I don't know, a 20% increase in capacity. But if we look at vehicle automation as we have it today, lower levels of automation, ACC, specifically ICE ACC, internal combustion engine ACC, at 20, 40, 60, 80, and 100% ACC vehicles, what we see is that fundamental diagram collapses. Remember, the two important quantities here were our maximum sustained flow and the density at which that, that transition from free flow to congestion occurs. And what you see here is the more ACC vehicles we have, turns out they're much more conservative. They're much more lead-footed. They hit the brakes harder. They're safe. They're comfortable. I don't blame car companies at all. But they are not designed or not implemented in a way that is friendly to a traffic engineer with traffic flow considerations in mind. And so you might see, I don't know, a 30% or so reduction in capacity. So that means that your 3-lane highway just became a 2-lane highway. And all that happened was a bunch of people turned on ACC. So if you're a traffic engineer, that is potentially problematic. All right, so at this point, the vehicles we have, likely the autonomous vehicles we have, likely will not actually bring us to that promised place of congestion-free traffic. However, I want to talk a little bit about what it might take to get there, and what it might take to actually change the vehicles we have, drive the vehicles we have slightly differently, with the objective of, not necessarily the objective of sort of looking at the occupant of the vehicle. Obviously, we still want to look at the occupant of the vehicle, still want to make sure that the car is comfortable and safe to drive in, but also add in the additional piece of information of what's the overall traffic flow like, and how can we improve conditions on the overall traffic flow? And so to do this, I want to start with a model of a human driver. Honestly, it's a very similar model. It's just a slightly more complicated. Instead of a constant time gap, it's a variable time gap that depends on distance, or it's a variable time gap that depends on the distance. And I want to start with a human driver model because ideally autonomous vehicles ought to drive similar to human drivers, or as similar as possible, but a little better. And what's that a little better? Well, the easiest thing that you could think of is probably something like you have some ideal speed that you want to drive. You know what the local density is. So you have some optimal speed that you want to drive based on that. And you do some sort of feedback control to push you towards that, right? Pretty straightforward. You can look at that same ring road setup, set it up. Your state is now the speed and spacing of all the vehicles on that ring road. And you can set up your linear system. If you do pole placement, if you increase your gain high enough, you can get all your poles on the left-hand side of the plane. The system is controllable, not a surprising result. But in theory, if you get the vehicle to drive with, in theory, what does that really mean? The intuition here is increase your gain, which is basically just saying, forget about speed up, slow down because the vehicle's in front of you, and just drive at a constant speed. So if you just drive at a constant speed, and you pick that speed correctly, and again, we can have a long discussion about what that means to pick that speed correctly. Just pick that speed correctly, and you can already make a lot of it. All right, so unfortunately, that type of controller is very difficult to implement on a self-driving car. So we work to do something that is very similar. I'm not going to go into all the details here just because I think what's really important is the intuition. The intuition is drive at a constant speed, at the right constant speed, unless local safety constraints tell you to do otherwise, unless you're going to get too close to the car in front of you. And we tested this as part of work I did a couple of years ago as part of a funded study with collaborators at the University of Arizona who had a self-driving car. What I wanted to show you is the video that resulted from this. So we're starting with that same ring road setup. The vehicle with the arrow on top of it is an autonomous capable vehicle. We have 21 cars in this case on the road. All of them are being human driven at this point, but we can hit a button to implement that or to run that controller on that vehicle. Now, if you look at the bottom, this is the speeds of the vehicles. And you can see relatively quickly that stop and go wave started. At this point, we've turned on the autonomous controller, and what that vehicle is doing is exactly what the intuition of that controller was. Drive at a constant speed, the right constant speed, unless local conditions tell you to do it. And what's really nice about that is it does open up a gap, but then it uses that gap as a buffer when the vehicle's when it hits the back of the wave, and it basically sends backwards a smoother signal for the vehicles behind it to follow. And so by the time you get 20 cars up the line, sure, you're introducing, each driver adds a little bit of oscillation, but it's not quite enough. So this is like 1 in 21, about 5% of traffic driving differently potentially is enough to bully in a good way the other 19 or 20 drivers to drive better. Cool thing about this is the other drivers had absolutely no idea that there was an autonomous vehicle there. We hired people and said, we're going to pay you to show up at this parking lot. This was in Arizona. Show up at this parking lot at like 6 in the morning because it's July in Arizona. That's very early in the morning. We will pay you for 2 hours to drive in a circle. They had no idea what was going on. The only person who was in the know was the person in the vehicle that was right behind the AV. Sorry, right? The people who were right in front of and right behind the AV. And it was just more in case something crazy happens. We want to make sure that these are trusted drivers who know what's going on. All right, so you can look at the space-time diagram. Traffic engineers love to look at these. We got time on the horizontal axis, position along the road. Each of these lines is the trajectory of the vehicle, right? The more horizontal it is, the slower it's going. The more vertical it is, the faster it's going. And the red vehicle is our autonomous. You can see if you compare over here that when we have traffic waves, to over here when we're actively dampening those waves with just that single autonomous vehicle, we have you can see much smoother traffic. We also had, this is where that thing is going to be a problem, but we will talk through it. We also had OBD2 scanners on each vehicle, so we're getting not super high fidelity measurements of things like fuel consumption and onboard characteristics of the vehicle, but relatively good sense of what the fuel consumption is. Obviously, we've decreased total braking events. That's not surprising. Got rid of stop and go waves, fewer people braking. What was surprising to me was that we saw a nearly 40% reduction in fuel, not just for the AV, but across the board. Now, if you worked on the next car project here, based on the conversations I've had here with folks over the last day and a half, that result is not surprising to you either. It turns out if you get rid of these, stop and go, you are moving from the most inefficient way to drive to the most efficient way to drive, right? From a fuel consumption standpoint. And the cool thing is we're actually doing this with a little bit higher throughput, about 15, 14% higher throughput. Vehicles are moving a little bit faster. It's not huge savings, not huge gain, but again, if you're a traffic engineer, your 6-lane highway became a 7-lane highway for free by just having a couple of people drive differently. And so that potentially could do something for it. All right, so to recap what we've talked about so far, the dynamics of individual vehicles matters. How individual vehicles in the flow behave impacts the emergent properties of the flow. It impacts what that fundamental diagram is going to look like. And up until now, the way we've done traffic flow management, if you look at most traffic flow management textbooks, you assume a fundamental diagram based on, the last 20 years of data. But it turns out that who's there determines what that fundamental diagram looks like. And if that's what you're building your control on, you want to make sure that you get that fundamental diagram. So my vision for the future is to fight congestion with the AVs you have, not the AVs you want. In the short term, we might have worse or less effective AVs or less efficient AVs from a throughput perspective. And that's okay. But what we need to know is who's there and how they're behaving so that we can get a good estimate of what that fundamental diagram looks like and then update our control or our control set points really for that fundamental diagram. I don't want to reinvent the wheel. We spent billions of dollars investing in our nation's traffic control infrastructure. If I tell you all of that is garbage, we need to completely tear it out and do something new, that would fall flat. That would never happen, right? Instead, I want to use data to make it a little smarter and a little more responsive to who's there. So there's sort of a couple different parts here that are necessary. First, we need to identify who's driving on the road and figure out, is it an AV, is it an ACC vehicle, is it a human driver? Then we need to figure out what that mix of traffic behaves like when you look at the fundamental diagram. And then we can update our control. What I'm going to be talking about here today is ramp metering control, perimeter control, where you're controlling the inflow into the ramp or into the highway. But in principle, you can apply this to any number of traffic control. All right, very briefly, identifying who's there. This is something that I'm going to just very briefly talk about today, just because I want to get to something else. But the basic idea is we have cameras everywhere. And the way an AV drives, it accelerates. It's the same stimulus, same car braking in front of it. It behaves differently from a human driver. And so what we've done is we've done a couple of different, relatively naive neural network type approaches where you look at, you build an LSTM or something to predict, is that an AV or is that driving like an ACC vehicle or is that driving like a human driver? Turns out that is actually relatively straightforward. Human drivers have much more variability in their behavior, and so you can even identify, is this a Toyota Camry or is this a Nissan Rogue? Because they have different ways of reacting to the same speed up and slow down. All right, so let's pretend that we have this and it works perfectly. We know what each vehicle is. The next thing is we need to model those aggregate flow dynamics. The way we're going to do this is we're going to basically go back to the car following models and assume that we can calibrate relatively accurate car following models for each vehicle. That's how we started the talk. And then kind of take those to the limit and look at them in the continuum to look at what that behavior is at the max. All right, so at equilibrium, remember that equilibrium flow is we have no acceleration. We've got some sort of speed spacing relationship. And so what we can do is for the we can basically come up, use that then to come up with a density based on the speed, and then use that density because the density is just 1 over the spacing, and then use that density and the property that we talked about before, where our density is our average speed times our our flow is our average speed times our density, come up with a flow density in congestion. In free flow, what we're going to assume is that all the vehicles just drive at the speed. All right, and then we can do the same thing for the automated vehicles. And basically what we need to do is the automated vehicles, again, are going to have our uncongested flow and our congested flow. And I'm skipping a couple of steps here, but basically, if we have that fundamental diagram for the automated vehicles, what we now need is a composite that's based on sort of the average, how many automated vehicles and human drivers do we have. So we've got some sort of gamma, which is going to be a parameter that tells us sort of what the percentage of vehicles that are automated, and we can use that to compute a weighted average, or a weighted average spacing rather, and then we can use that weighted average spacing to compute the weighted average density, and then we're off to the races again, and we get a density that's not just a function of the speed, but also of the percentage of vehicles that are automated. And so then what that gives us at the end of the day is a flow density relationship, fundamental diagram that, again, previously you only had density in there, but now we're looking at mean density and the percentage of vehicles that are automated. And so we get something that looks like this. So if we assume that the human drivers follow an IDM, pretty common, the automated vehicles follow an OBRV. In free flow, again, everyone's driving together at the speed limit, but in congestion, what matters is what the percentage of vehicles that drive with the IDM that are human, and what's the percentage of vehicles that drive with. So instead of that typical, two-dimensional fundamental diagram, what we now have is we've added a third dimension, which is the percentage of vehicles, the market penetration rate, the percentage of vehicles that are automated. And so at any particular market penetration rate of automated vehicles, we can take a slice, and that's our current fundamental diagram. Those are sort of the simulation plots that I showed. Now, in this case, I picked a pretty extreme example, a very aggressive vehicle or very conservative vehicle that greatly reduces the capacity, but just to sort of make a point. But in reality, depending on what two species or what multiple species of traffic you have, you could come up with different fundamental diagrams. All right, so the last part then is how do we use this to impact the control of traffic? And specifically, I want to do ramp metering control. The key to ramp metering control is really just you don't want to get into the congestion. So the goal is to keep the main to use the stoplight at the on-ramp to prevent the flow of traffic in, so that you prevent the flow on the main line, on the highway, from exceeding your critical density. That's the whole intuition. There's a lot of different algorithms to do this. The most popular one that I've seen sort of the literature is one called Polinia, which basically is a linear feedback control. You look at the density on the main line, you look at your optimal density, you look at the difference, and that's how much you can allow on from the ramp, right? It's pretty straightforward. Does it work? Turns out it works really well. The Twin Cities of Minneapolis and St. Paul, where I live, are sort of oftentimes cited as the poster child for this. We've had ramp metering since the 70s. People didn't like it. And so in the early 2000s, the state legislature mandated MnDOT, the Minnesota State Department of Transportation, to shut them off for a 2-week period to observe what happens. And it turns out that when they turned them off, they saw that uncontrolled, they had, well, rather controlled, they had about 55% reduction in fuel consumption. And also travel time went, or when they turned them off, travel time went off. I don't remember the exact number, but travel time went up something on the order of 20 to 30%. So they do make a big difference. They are very effective. And again, the most common, all of them are some form of feedback control. The most common one is a linear, which is just a simple proportional feedback control. You've got your actual density, your actual critical density, and you've got your target density and your current density, and you look at how far from that you are, and you can update your ramp flow rate from there. Now, in simulation, what I want to consider is 3 different scenarios. First of all, uncontrolled. So this is no ramp meter, just uncontrolled dynamics. Second of all, I want to look at controlled dynamics, but where we assume a fixed fundamental diagram. This is sort of legacy control, right? This is what we're doing today. And then the third one is controlled dynamics, where we consider what's the current market penetration rate of vehicles? What's the current mix of vehicles at that moment in time? In order to do this, we need to have not just dynamics on the density, but we also need to have market penetration rate dynamics. So what's the percentage of AVs at every point along the road? In the interest of time here, I'm just going to sort of skip to the simulation that shows these three different cases. And a common metric here is total delay. And if you look at the uncontrolled versus the controlled, the wrong controller versus the controlled with the correct updated dynamics that depend on who's there, you see a roughly 25% reduction. So what that means in this case, when we have vehicles that are worse, we could potentially see an improvement. In the other case, when we have vehicles that are better, that fundamental diagram for the automated case might be even bigger. And so we could be throttling ourselves. But if you update dynamically the fundamental diagram, you'd actually see that you could, increase the outflow, and you could get more capacity across the road because you're looking at basically you have a fundamental diagram that's bigger with a higher critical density and a higher flow, so you match that. All right, so I think the theme so far has been individual vehicle dynamics, change the flow. We can do this for better. I'm going to briefly mention another direction that I've spent a lot of time thinking about, and that is you can also potentially do this for worse. It's more of a cautionary tale, but if one vehicle drives differently, that totally changes the flow. 5% of vehicles drive differently, that totally changes the flow. That makes me nervous because with vehicles getting things like over-the-air software updates, you can imagine a case where there's an over-the-air malicious software update that goes out that causes them to drive worse. Now, obvious cyber attacks, there's a lot of examples of these. Vehicle drives off the road, vehicle crashes into another car. I'm concerned about these because they're bad, but they're also really obvious to detect. All of a sudden, all vehicles from a certain make and model started doing this. It would be obvious. But a subtle cyber attack, or what I call a stealthy attack, only slightly perturbs the way vehicles drive, making them only slightly worse drivers, but could potentially cause congestion or even worse, cause additional traffic. I've come up with a whole bunch of different sort of ways to do this. Most of the work basically focuses on let's take the ODE vehicle and let's inject something into that ODE. Happy to talk about this more offline if you're interested. The results are kind of wild. It turns out that you don't need to inject that much noise or that much of a malicious signal to have vehicles, not the vehicle that's tagged, but vehicles 10, 15, 20 vehicles down the line cause a crash, and they don't even and you can't even tell who it was. All right, so that's just sort of I know that there's some folks here who think about cybersecurity vehicles. I think this is another aspect that not quite as scary as driving off the road, but could potentially be very difficult to do. Okay, so in summary, increased vehicle autonomy, I think will change the way traffic flows. Short-term trend, that might mean long-term trend might mean increased capacity. But in the short term, that might mean decreased capacity to the current generation of vehicle automation. Cool thing is that once you start to talk about electrification, different powertrain, turns out the powertrain you have impacts the flow dynamics. And so there's this sort of linking between very low level vehicle level things and very high level traffic flow level things. But all of this is sort of benefits, all the things that I've seen so far, benefits to the individual drivers. We ought to start thinking about benefits to the flow overall. And that sort of brings us to, what if we can leverage knowing who's in the flow, knowing what vehicles are in the flow, and use that to modify legacy control. And it turns out even simple things like updating the way we do ramp meter, a pretty standard tool for traffic engineers, has the potential to lead to pretty substantial reductions in travel time if we see these sort of current generation automated vehicles continue to. All right, it would be unfair for me to say this was all my work. This is really my students' work. So 2 former students and 3 current students who spent a lot of time on this, as well as a lot of undergraduate students, external collaborators who I think I might have gone a few minutes over, so I apologize for that, but I'm happy to entertain any questions if there's still time for that.
So we have about 24 people online.
Thank you for joining online.
I can monitor the question. So if you're online, if you want to ask questions, you can type them in. I don't think you can unmute yourself, so you can type in the chat and I'll take a look. Any question? Yes, do.
Hello, thank you for the talk. I'm wondering, in the modeling process, where does merging across lanes come in?
Yeah, so everything I talked about was longitudinal control, but when you start to think about highways, you need some sort of lane changing model as well, some sort of lateral dynamics. For the most part, I just use off-the-shelf models because my thinking is for the automated vehicles, sure, they might do stuff differently. And there's a whole ton of work on cooperative lane changing and things like this, which could really, I mean, what is a lane change? It's really just a sharp perturbation in that string, right? You have a string at equilibrium and a vehicle cuts in, that's just sharp perturbation there, either in spacing or in speed. And so absolutely, there's stuff there if you have connectivity that you could do. But for the most part, when we look at these low-level vehicles, my assumption is still the human is doing the lane change. And so the lane changing models that others have built, I don't think I can do better than that. And so I just use the off-the-shelf models. But absolutely, absolutely something that needs to be thought about for the higher level of automation.
Yeah. In that simulation where you showed that if there is one malicious vehicle who does like a stealthy attack, then you have sort of chaos dynamics, right?
I don't know if it's chaotic. I'm not sure I have the mathematical background to say if it's chaotic, put it that way. But I mean, what we're doing in this case is we're just injecting noise. Because we don't want to, because I don't know a better, right? Like we didn't, the goal of this was not how do we attack vehicles the best? The goal of this was, what if we even just do something pretty simple? What does that, like, again, my interest is always, what does that mean for the traffic flow? And so we're just injecting noise at the control level. Now, of course, you can imagine there's noise at the sensors as well. You can inject noise at the sensors, et cetera. Or if there's communication, then you could imagine the command in the middle type attack where you inject noise into it injects intentionally false measurements or potentially false transmissions from other vehicles. But in this case, we're looking at just sort of individual vehicle that gets that has some sort of software update to slightly perturb the controller, make it slightly less stable. And as we saw, if vehicles drive slightly worse, you may not notice it as a driver, but it could have traffic flow level impacts.
And like, could you control this sort of a like rogue vehicle with another vehicle by sort of like, pulling that rogue vehicle using some
and then like get it to do probably. Yeah, I haven't thought about that, but probably, yeah. Now, of course, the challenge is identifying who the rogue vehicle is. And that's part of the thing is that you don't, it's very difficult in a case like this, it would be very difficult to identify who the vehicle is. Just because they're not doing anything that's wildly different. They're just doing something that's a little different. They're just slightly worse drivers. But yeah. So I think localization of the attack would be really challenging. Yeah.
How did you pick the density for the ring road experiment in Arizona?
We wanted something. We tried a bunch, and it turns out that almost regardless of the density, so long as you're not totally in free flow, you're going to see the waves.
So past peak vertical.
Yeah. Exactly. Yeah. You're close. You got it close, right? We did it 30 some odd times at different densities. Take off cars, add cars, go. It's just a matter of how complicated. And so then for the actual experiment, we were like, let's just recreate the Japanese experiment, just because that's well known. And so we said, let's just redo that ring road experiment basically. And so that's why we had that density. Now, the one thing is they did theirs on a 230 meter track. We started that. Go. You notice two differences between this and the Japanese experiment. The one is the one is that we're on 260 meter track instead of 230, and that's just because the vehicles were University of Arizona motor pool vehicles and are like substantially larger than the vehicles in Japan. The other thing is, I believe you'll notice that here we're going counterclockwise, and the video in Japan going clockwise. And that's because it turns out that you want the human, if you want to have them follow a line of cones, this is sort of very much just like, how do you pull this off? You want the humans to be on the inside, the driver to be on the inside. In Japan, they drive on the left side of the road, so the driver is on the opposite side of the vehicle, and so you need to actually change the direction of the experiment. Like humans, exactly. It turns out you can do what you want, but you still have to engineer the human.
Yeah. So I have a question online. What are some of the pros and cons of AVs to manage traffic versus using more public transit? And what about automation in public transit? So how would the automated public transit, like buses?
Yeah, great question. Excellent question.
Then automate, like,
yeah.
Can I rephrase that? Can I ask an add-on question? Would the fundamental diagram change for a public bus and an automated bus and an automated?
I don't. The answer is I don't know. The answer is I don't know. At the end of the day, when you look at the fundamental diagram, there's just not enough buses on the road to really greatly impact that, right? We're looking at 2,000 vehicles per hour per lane is a pretty typical max of that fundamental diagram. And if you have bus service even every 5 minutes, you're just not getting close to sort of making it down there. On the automation in buses versus automation in cars, I mean, I still maintain that actually the most logical first use case for full automation is long distance trucking, because that is where you really have very standardized conditions on the highway, right? And there's very standardized conditions, very limited access. You don't typically have children playing at the side of the highway, things like that. Only one direction of travel. You don't have intersections. You only have on-ramps, and then you perhaps have a driver who sort of meets the truck when it gets close to the city and drives the last mile. And that's where automation is I think, could potentially really make it happen. The other thing to keep in mind there also is that when you're talking about automation, I think many companies have tried to do automation with cheaper sensors, but the limiting factor is still the cost, both of compute. That has come down a lot, but it still requires a lot of compute and of sensors, right? And we've seen how successful or unsuccessful only rely on cheaper sensors. Ideally, most of the companies that sort of do this on a very large scale or want to do it at a large scale rely on sensor fusion across multiple different sensors. If you're spending, I don't know, $50,000 to $100,000 on sensors, compute, and a software stack, that's not feasible on a $30,000 car anytime soon. But if you're paying $250,000 or something like that for a truck that's being utilized, if you're driving in shifts 20 hours a day, that's much better utilization versus my car, which is parked on a day that I drive a lot. I drive, right? So it's parked 90% of the time. In terms of automation versus transit, that's tough. That's a human behavior thing, right? We've seen post-COVID, in the US at least, most transit agencies have seen a decrease in ridership even after return to work. A lot of that is people don't like transit. It's like I mean, I ride transit. I commute by transit every day, right? But a lot of people, so there's a lot of good reasons not to take the bus. Mobility concerns, right? Where if you have, you got to drop off a kid here, pick up someone else here, do grocery shopping, and get to work somehow all, and you can trip chain that might be very difficult. So I think the focus ought to be those people who can move trips to transit ought to be incentivized to move trips to transit, because ultimately, if you think about sort of what will happen to vehicle miles traveled, this is the part that I'm really concerned about. I can engineer, 20% more efficient roads with better driving vehicles, but if people drive twice as much, there's no automation engineering that I can do to overcome that. We're going to have to build roads, and that's also not a great solution. So I think, I think the answer is we need to. Yes, please. We need to work on that. I don't think I have the answer there, but it's absolutely something that needs to happen. Otherwise, red flag.
This might be a little outside the scope, I'm not sure.
Yeah.
Anecdotally, I've noticed people also behave differently around ACC and autonomous vehicles. There's a lot more frustration maybe going around or cutting off because they're not used to those safety buffers that other drivers might normally ignore.
Yeah.
Have you seen any of that in the longitudinal studies as well, or is that more of a
I would love
kind of
you to say, I would
two-dimensional
love
problem?
if you had said not anecdotally, but in the data I've seen, because I would ask you, can I have that data? This is actually something that we were talking about yesterday. I'm sure. Anecdotally, there's a lot of reports, especially when like Google was doing the, starting in California, and people were like seeing what they could do, like seeing how much they could sort of, intimidate the car to do something, but also just really frustrated with the fact that speed limit's posted at 30, but the car's going 20 because it doesn't feel comfortable driving at 30 there or something. And a lot of frustration. I think that's less so the case with ACC, because generally ACC is sort of, okay, sure, maybe it's a little more conservative, but it's relatively difficult to tell if it's an ACC or not. But I think with automation, that could potentially be an issue. And I wish I had the data. There's one data set that I'm aware of, was just recently released, the third generation simulation, so the next generation simulation data set, I don't know if you're familiar with it, that was collected in the early 2000s by the Federal Highway Administration, really to calibrate these car following models for human drivers. It's trajectory data of people on somewhere in California, on I-80, I think, outside of San Francisco, as well as US 101 in Los Angeles. And then the newest data set is the third generation simulation data set, where they had different levels of automation driving on an urban highway, I think in Chicago, on 290 in Chicago, and they filmed it by helicopter, and they looked at the behavior of vehicles.
I see. But again, maybe not anecdotal, but not big. So there was Delphi testing some autonomous driving technology.
Okay. Yeah.
So come from the other perspective. So they were testing the autonomous driving technology, and as they were deploying the vehicles, they realized that the vehicles surrounding them, they were doing weird stuff the moment they realized there was nobody driving. And so they put in fake drivers.
Like a dummy driver.
Like the person there holding,
Make it look
like they were driving. Otherwise, the interaction with the surrounding traffic was skewed by the perception of the drivers. And so you couldn't know, like people slowing down and be like, look, nobody's driving that car, right? And then thinking, not cutting in front that closely because they were afraid or things like that.
The other study I've seen, which is sort of the opposite of this, is they tried to fake automation. And so they had the person, this was, I think, done, I want to say, they had the person dress up like a car seat and then drive, with their hand at the bottom of the steering wheel. So it looked like
they had a clown steering wheel, like this big, and
and then they're driving. Okay. And so they're like literally, there's a picture of the person dressed up like a car seat. But I don't remember what they found. But yeah, I think there is an impact, and it's super interesting. I think this is absolutely an interesting direction.
It's well recognized there is one, but we don't measure.
My thought is it just like add to that effect of the autonomy kind of making the traffic flow a little worse.
Potentially, yeah. If people, I mean, there's a lot of instances of people taking like traffic cones, right? Like coning it's not Waymo. Which one was Cruise? I think it was a Cruise.
I remember hearing about
We put a cone on it, and so then it sees a cone, looks like a rhinoceros, and it stops in the middle, right? And so there's a lot of, I think people are going to try to take advantage.
Yeah, that's the other problem. Like the moment that people realize it's an autonomous vehicle, they tool around it. So it's not, yeah.
Yeah.
I think it's worth.
that.
But
Going around and painting white stripes
Oh,
around.
so it's stuck.
Yeah.
So it's stuck.
So you couldn't pass the white lines. Yeah.
all right. Well, let's thank some of you.